Okay, we're ready to handle what happens when we don't know what the population standard deviation is, which is what's going to happen most of the time in practice. I mean, so generally when you're studying something, you can take a sample, you can kind of estimate the mean, but it's not going to be clear what the underlying population standard deviation is in practice, right? That's very rare. If you know the underlying population standard deviation, you generally know everything about the population, and then we're back to descriptive statistics instead of inferential statistics. So that's a slight oversimplification, but most of the time we're not going to know sigma. So what we need to do is use what's called the T distribution. This is called students' T distribution. This distribution has a little bit of a history behind it. This was developed by a mathematician, well, a statistician named William Seeley Gossett. He was a brewer, he worked for Guinness, and he was trying to sample, he was basically trying to take samples of beer and analyze them statistically. His problem was that he was trying to work with really small samples of data. So say you had 2 or 3 or 4 batches of beer and you didn't have a huge data set to choose from. He kind of figured out how do you deal with a small data set. And it turns out that there's this distribution now called the students' T distribution that he developed. The reason it's called the students' T distribution is that as a employee of Guinness, apparently at the time Guinness had a strict rule that if you were employed at Guinness, you weren't allowed to publish any research as an employee. So what he did is he published it anonymously, and he just called it students' T distribution, just as a generic student. And so that's why it's called the students' T distribution, but it was really just developed by William Seeley Gossett. So this is a distribution, and it's going to behave in a lot of ways like the normal distribution, except there's going to be some differences. So first, let's talk about the similarities. It definitely looks a lot like the normal distribution. It's symmetric. It looks bell-shaped. It's not exactly, but it looks pretty good bell-shaped. It turns out that the shape of the distribution is going to depend on what's called the degrees of freedom, which we're going to denote by df. And so the degrees of freedom is going to be the size of our sample minus 1. So in our case, if we have, in our case that we were working with before about the data analyst starting salary positions, we had 10 salaries that we were looking with, so our n was 10. That means that our degrees of freedom are going to be 9. The idea with degrees of freedom is imagine you have a data set, and what you're told is, so imagine that you have 5 numbers, and what I tell you is pick any 5 numbers whose mean is, say, 10. The first 4 numbers can be whatever you want them to be. Okay, they can all be 2s, they can all be 20s, it doesn't really matter. But if you know what the mean has to be for the entire data set, that 5th one is fixed. So that's the sense where you have 4 degrees of freedom, right? 4 of those variables are free to be whatever you want. And then the last one is fixed if you wanted to have that additional property that it has a prescribed mean. So that's why the degrees of freedom is n minus 1. This is a concept that we will run up against a few different times in the course of our semester, okay? But this is the first time. So for now, the degrees of freedom is just n minus 1. And this T distribution has this is the table that we were actually looking at before that had the Z values in it. So let's actually look at the table. And so this T distribution, I'm sorry, this is the normal distribution. We'll come back to that. I knew that this was the normal distribution, by the way, because first of all, it says standard normal, but also it had the Z value. We know that Z is our standard normal. So the T value, T sub alpha, is again going to be, it's the same notation. T sub alpha is the cutoff point at which under the curve, that area, that region has area alpha. So this is the cutoff point so that the area to the right of that cutoff point is alpha. So that's the same notation that we had before. It's just for this new curve. I'm not even going to tell you what the formula is for the T distribution, but you can search for it if you'd like. And again, this is not going to be exactly the same table that we had for the normal distribution. This is kind of just the highlights here. But this is just a table of those cutoffs, T sub alpha. And so we're working with a data set of size 10, that means that our degrees of freedom are 9. So for us, what we're doing is we're working with that row right there. So when we have 9 degrees of freedom, those are going to give you the various cutoff dates, the various cutoff values, I should say, t-values. Now, when the number of data points is large, and this is an idea that we saw previously in the central limit theorem, but when the number of data points is large, then you can essentially just approximate everything with a normal distribution. And so that fact is why the z cutoff, the z sub alpha values are at the bottom of this table, is that as the degrees of freedom is increasing, so notice that there's 50, 60, 70, and then it starts jumping by 5s, then by 100s, and by 1000s. And notice that the values actually themselves aren't changing very frequently. So as n gets larger, the t-distribution is going to start to look more and more like a normal distribution. So you can kind of think of these as, right, if you had infinitely many degrees of freedom, or equivalently infinitely many data points, that's kind of why these are kind of viewed at the bottom of that chart. You could think of these as limits. And you can indeed look at the numbers here. You have 2.576 versus 2.578. Okay, so those numbers are really close. And that's the same for all the way across. So this is, again, a very quick introduction to the t-distribution. And the reason why we need that is that we're going to talk about a few things here. So the first thing, and I'm going to just kind of word this slightly differently than we did before. Let me actually jump to the chapter 8 formulas, because I think they can all make sense now. We talked previously about the standardized version of the variable x bar. So that was the mean, that was our x bar minus the population mean over our standard deviation, which was sigma over square root of n, where we're talking about a sample of size n. The confidence interval had this formula. Okay, so that was the sample mean plus or minus that formula. The margin of error we talked about. The sample size for estimating mu we talked about. That was where we squared both sides and solved for n. And what we're going to do is we're going to use the t-distribution in the situation where we don't actually know what the underlying population standard deviation is. So that's where the t-distribution is going to be useful. But otherwise, it's the same process. So we're going to, instead of looking at the standardized, we're going to look at what's called the studentized, because it's the student's t-distribution, but the studentized version of the variable x bar. So it's going to be the same formula, except basically you replace all the z's with t's, and you replace all the sigmas, because we don't know what the population standard deviation is necessarily, but we're going to replace that with the sample standard deviation, s. So that's the standard deviation of our sample s. And likewise, the confidence interval will be the same. You replace the z's with t's, you replace the sigma with s. Other than that, everything's the same. Okay, and again, just keep in mind that which t-distribution you're going to use is going to depend on your degrees of freedom. Okay, so your degrees of freedom is going to be n minus 1. Okay, so what we'll do is in the next video, I'll show you this t-distribution is super useful in R. There's a nice way that we can just plug in all the data. R does everything for us. It's super nice, and I'll show you how that works in the next video.